Welcome to the massive open online course on Aspen Plus. In today's lecture, we shall learn about the simulation process of reactor models in Aspen Plus. If you look at the simulation window of Aspen Plus, you will find the following blocks for the reactors. These are the blocks you will find: R stoic, R yield, R equal, R Gibbs, R CSTR, R plug, and R batch. These blocks can be subdivided into three main categories. R stoic and R yield, they come under the category of balance and stoichiometric based reactors. Equilibrium based category, they have R equal and R Gibbs model blocks as given over here, and these three are common reactors that we all know. RCSTR, that is continuous star tank reactor, this is plug flow reactor, and this is batch reactor, and these three, they come under kinetic model based category. So we will learn them one by one. First we will learn this balanced or stoichiometric category, then we will learn equilibrium based category, and then finally we will learn kinetic model based category. First is R stoic block. This block models with a specific extent of reaction, also known as conversion. So suppose you are having a reactant A and B, and if you say that this reactant A will have a conversion of 97%, then that information can be given into this R stoic block. Then models where reaction kinetics are unknown but stoichiometric is known. It performs the product selectivity and heat of reaction calculation, and it can either run simultaneously or sequentially. On the other hand, R yield block does not need any kinetic or sizing information, but it works on some yield basis. The yield basis can be either molar or mass. That means number of moles of chemicals leaving through the outlet per total mass of feed, and mass basis it is mass of the chemical leaving through outlet per total mass of the feed. You can say mass fraction. R yield satisfies the total mass balance, not the individual component balance. Sometimes it gives a warning message that says it has scaled up or scaled down the molar or mass basis such that the total outlet mass flow rate is still equal to the inlet mass flow rate. We will learn it better when we do the simulation. And finally, it as such does not satisfy the first law of thermodynamics. So it is always an approximation sort of. The R equal block, it is useful for modeling a reversible reaction, assuming that it nearly achieves chemical and phase equilibrium. It calculates the maximum thermodynamically possible conversion one can achieve based on the reaction condition. So it is wise to use sub-equilibrium condition at an approach temperature. We'll learn about the approach temperature later. It computes the equilibrium constants directly from the Gibbs free energy of the reaction at the temperature of the reaction condition. And it calculates the outputs using equilibrium coefficient combined with mass balances, energy balances, and flash calculation. And most importantly, it requires the separate outlet ports for liquid and vapor. For other reactors, there is no separate port for vapor and liquid, but in this block, you have to have separate ports. And then comes R Gibbs block. It does not need to specify the equations. Given infinite time for a reaction, the chemical equilibrium is achieved when the product mixture reaches its lowest possible Gibbs free energy. In other words, this block calculates what is the maximum extent of conversion that a reaction can achieve. Through a complex algorithm, R Gibbs block solves an optimization problem that finds the exact outlet mixture which has the lowest possible Gibbs free energy. And definitely the first law of thermodynamics holds in this calculation. Without that, we cannot get the minimum Gibbs free energy calculation. So we shall learn about these 4 blocks which I have talked about: R Gibbs, R yield, R equal and R stoic, using this small exercise with water gas shift reaction. As we all know, water gas shift reaction is about reacting carbon monoxide with water at 360 degrees centigrade and atmospheric pressure to achieve hydrogen and carbon dioxide. The flow rate of carbon monoxide and water is given, and we shall use Peng-Robinson equation of state with Boston-Mathias property methods. For R stoic and R yield, we need this information, 92% of conversion of carbon monoxide, whereas an approximate approach temperature has been given for R equilibrium, which is 253 degrees centigrade. So we need this information for calculation. So let us see how these blocks can be used for calculation in Aspen Plus simulation window. So for that, we need to specify the components. So our components are carbon monoxide, carbon dioxide, water and hydrogen. Press next. We have to use Peng-Robinson equation of state with Boston-Mathias property methods. So we get it here, Peng-Robinson equation of state with Boston-Mathias modification. So we press next and run. So property estimation is complete. Go to simulation window. We directly go to the flow sheet. So in the reactor, first we bring R stoic. This is the material stream and this is the product stream. We name feed and here we name P stoic. That is product from R stoic block. Press next. We have to give the temperature of feed. So this is 360 degrees centigrade and 1 bar pressure. And we have 500 kilomole per hour water and 100 kilomole per hour carbon monoxide. So press next. Now it is asking for the inputs for R stoic model. So temperature and pressure we have to specify 360 and 1 bar, and the reaction. So reaction we have to press new, and here component CO, carbon monoxide, reacts with water to form carbon dioxide and hydrogen. So coefficient -1 because they are reactant and these are products. And fractional conversion has to be given, which is 92% conversion of CO. So 0.92 of CO. Press next. Now it is ready to run. So run. The result is available. Go to stream results. So here you can see in the feed we had 100 kilomole per hour of carbon monoxide, but in the product of stoichiometric reactor we have only 8 kilomole per hour carbon monoxide. So 92 kilomole per carbon monoxide has been converted into carbon dioxide. And similarly, due to stoichiometric equivalence, 92 kilomole per hour of hydrogen has been produced. Now let us see how R yield works. For that, let us go to main flow sheet once again. Bring in R yield over here. We shall use the same feed over here. So let us first use a manipulator. Here is a duplicator. We shall connect this line with the duplicator, and then we'll do the material stream connection between duplicator and the reactors. And we have to rename it. Let us rename it as P yield. Now press next. Feed has already been defined, so is the R stoic. So R yield has to be defined here. So temperature is same, 360 degrees centigrade and 1 bar pressure. The yield has to be specified. Component yields. Now here we have to check whether we want to give it on molar basis or mass basis. In my opinion, at least for this problem, watching mass basis is better because we already know the result in the R stoic model. Here, if you see mass fraction, then you will find that it is 0.0189761. So 0.0189761. Carbon dioxide, again mass basis, water mass basis, and hydrogen again mass basis. So carbon dioxide will have 0.342875, 0.342875, water 0.622443, and finally hydrogen 0.0157055, 0.0157055. So all the component yields are specified. So we can run the simulation. Now we can check the result once again. So we can place P yield side by side with P stoic to compare the result. Here we can find that there is slight changes in the values. Here you will find certain warning messages, that is a sign of this nature. So we can further explore what they actually mean. So for that, you go to the results and see status. Here it is said, specified yields have been normalized by a factor of this to maintain an overall material balance. So it is as good as the error message or warning message that I was specifying some time back. It scales up or scales down by doing certain normalization to make the inlet mass flow rate equal to outlet mass flow rate. Okay, so R yield, again, it is some kind of approximation and we have to accept this result in this manner. Anyway, so let us keep our result in this fashion only. We'll analyze it later. Now let us see how the R equilibrium block works. For that, bring in the R equilibrium, connect the material streams, and here you can see that we have to give two outlets. One is vapor, another is liquid, because that is the norm for any equilibrium reactor. Now let us write it as V equal and let us write it as L equal. Press next. We have to give the temperature pressure condition which are same as before. Then we have to specify the reaction. So the reactant are CO and water. Products are carbon monoxide and hydrogen. Coefficients for reactants are -1 and -1, whereas coefficients for products are 1 and 1. Here we have to determine the products by specifying temperature approach to equilibrium. Here one data has been given, 253 degrees centigrade approach temperature for R equilibrium. So 253 degrees centigrade if we give as an approach temperature and run, let us see what happens in the results block. So the results are available. Let us see what are the results. Here we write V equal and L equal. Now here you can see one thing, that is in L equal everything is 0. So this is obvious because at 360 degrees centigrade you won't find any liquid because you have CO, CO2, water and H2. So at 360 degrees centigrade none of them can be in liquid phase. So there won't be any liquid over there. Everything will go as a vapor. So that is obvious. Now in vapor phase, if we see the mole fraction of carbon dioxide is 0.159256, whereas with stoichiometric reactor it is 0.153333. The mass fraction of carbon dioxide calculated by the R equal block is 0.342031, whereas calculated by stoichiometric reactor it is 342875, and that is using 253 degrees centigrade temperature approach. Now let us try to see what happens if we increase the temperature approach or if we decrease the temperature approach. For that, let us change the data in input block. So we change it to 260. Now at this moment it is 342031. If we run and see what happens, so it decreases. If we make a higher temperature, then the value decreases, and if we take a lower temperature, obviously it will increase. So if we take, instead of 253, if we take 240, then definitely this will increase. Yes, it has increased. So we want to know at which temperature approach the value of CO2 will be exactly 0.342875. For that, we can do certain sensitivity analysis. Although I will teach the sensitivity analysis in some future lecture, but today for the example, it is important to learn how to do it. So for that, we have to go to this model analysis tool and say sensitivity analysis. So press a new, enter ID S1, and then type a variable new. This is a block variable. So we have to choose the block B5 because that is the equilibrium block. And the variable, let us look for the variable, what the variable is. We have to say approach, temperature approach. Let us see what is this. Yeah, this is the one, temperature approach to equilibrium. So delt is the one which we are looking for. Let us give an idea of 1 in degree centigrade, and we start from 240 degrees centigrade and end at 260 degrees centigrade with an increment of 1 degree centigrade. Then define a variable, say give a name of the variable, say V1. Actually it is a stream variable which is mole fraction of stream V equal and component, say carbon monoxide. Go to tabulate and fill variables, column number VA1. Let us run and see. Yeah, so run results are there. Just go to results. So you can see from 240 approach temperature, at 240 approach temperature it is 153768. So if you see mole fraction, it is 153768 at 240, and at 260 it is 152513. So actually we want the value which is very close to 153333. So which is the nearest value for 153333? It is 247. Okay. So let us redo this once again between 246.5 to 247.5. So go to input. So 246.5 to 247.5 with an increment of say 0.01 and run it once again. So results are available. So you can just go and see where exactly it matches. So here you can see 246.98, 246.99. At this temperature, the mole fraction matches with stoichiometric reaction. So we can use either of them, 246.98 or 246.99. So let us use 246.985. So go to block, input, reaction, edit it, give the temperature approach as 246.985 and run the simulation once again. Just go and check, and this is the result you get. Okay, it matches, everything matches with R stoic. So to achieve this amount of mole fraction in the product, that is the temperature approach for equilibrium. Okay. Finally, R gives. So for that, let us bring in R gives block over here, connect the materials, rename it to P gives, press next. Here we have several calculation options. We can ask for phase equilibrium and chemical equilibrium calculation. We can ask for only phase equilibrium calculation, or we can restrict the chemical equilibrium by specifying the temperature approach, or we can specify duty and temperature and calculate temperature approach. For this example, let us take the calculate phase equilibrium and chemical equilibrium option. Here we have to specify the pressure and temperature once again, and then everything seems to be specified. Just run the simulation and check the result. P gives yes. So here you can see P Gibbs has calculated the lowest point of Gibbs free energy. So this is the maximum extent of reaction that can happen. Like the carbon dioxide cannot be produced more than this mole fraction. In other words, there cannot be more than 98.72% of conversion. At this conversion, the Gibbs free energy is lowest for this kind of reaction. Now, if we want to limit it up to 92%, then what is the Gibbs free energy up to that point? That also we can calculate from here. For that, we have to choose specify temperature approach or reaction extent. And then we have to choose restrict equilibrium. And again, the temperature approach or molar extent for individual reaction. So press new, press CO, water, CO2, hydrogen, write -1, -1, 1 and 1. And here you can write 92 kilomole per hour. Or you can say temperature approach as it was said 246.985. That was the temperature approach we had given over there. So let us use this. Okay. Now you can run the simulation and check the result. And you can see the result with P Gibbs. Here it is not going up to 98% calculation. It is up to 91.999 and actually 92 you can say, because you have restricted the equilibrium. Now we shall learn the last three reactors, that is CSTR, plug flow reactor and batch. For that we open a new simulation block and we shall use this example of common reactors with known kinetics. In this reactor we have ethanol acetic acid as a reactant, and from them we produce ethyl acetate and water. The flow rate of the reactants and the temperature pressure conditions are given, and the reaction kinetics, the K value and activation energy are given, and we will use NRTL Renon Hayden O'Connell EOS with Henry's law. For CSTR, plug flow reactor and batch reactor, individual conditions are given. So with this information, we will see how these models can be used. So the components are ethanol, acetic acid, water and ethyl acetate. So we have ethanol, acetic acid, water and the product ethyl acetate. We have to find an ethyl acetate. We have to select this one. Just rename it to eth acid. Next, we shall use NRTL Hayden O'Connell equation of state with Henry's law. So NRTL, yes, it is here. NRTL Renon Hayden O'Connell equation of state with Henry's law. Press next, next, run. Yeah, the properties are calculated. Go to simulation block. So let us first take CSTR and the material streams and then rename them. This is feed and this is PCSTR, product CSTR. Press next. The temperature and pressure condition, it is 70 degrees centigrade and 1 atmosphere pressure. So 70 and 1 atmosphere. Ethanol and acetic acid 200 kilomole per hour. Water 10 kilomole per hour. So it is 200, 200 and 10. So this is the feed input. Go to next. So CSTR pressure, again it is 1 atmosphere and temperature 70 degrees centigrade. Valid phases, we have both vapor and liquid. The reactor volume is, we have to write 0.14137 meter cube. 0.14137 cubic meter. Now you may be curious to know what is the reason for giving such an odd value in the reactor volume. For that, we have to see the plug flow reactor. You may notice that the plug flow reactor, the length is 2 meter and diameter is 0.3 meters. So the volume of plug flow reactor should be pi by 4 into 0.3 square into 2. So if you calculate, this will be equal to 0.14137. So in order to compare the result, we wanted to keep the reactor volume same for both CSTR and plug flow reactor as well as batch reactor. Now we have to press the reaction kinetics. We don't have any reaction kinetics available. Now we have to go to the reactions and define a new reactions over here. So reaction ID R1, which is of power law type. So we have a power law equation with this. So say stoichiometric ethanol reacts with acetic acid to produce ethyl acetate and water. The coefficient should be -1 and -1 for them because they are reactant and they are product, so they are 1. Exponent will be 1 and 1 for them, and it will be 0 and 0 for them because they are product. Reaction type is kinetic. Now this is the forward reaction, but we have reverse reaction also. This is both ways. So we have to define the second reaction also, where the component ethyl acetate will react with water to produce ethanol and acetic acid. So here it is -1, and this is 1 and 1, exponent 1, and this is exponent 0 because they are products. And as because they are kinetic reactions, so we have to give the kinetic information over here. So the K values for forward reaction is 1.9 10 to the power 8, 1.9 10 to the power 8, and E value, activation energy, is 5.95 into 10 to the power 7 joules per kilomole. 5.95 10 to the power 7 joules per kilomole. So this is for reaction number 1, and reaction number 2. Again, it is in reverse reaction, it is 5 into 10 to the power 7, 5 into 10 to the power 7, and activation energy is same, which is 5.95 10 to the power 7 joules per kilomole. Now they are defined. Okay, so the reactions are defined. Now we can go to the reactor setup and define these kinetics. Now R1 is available. Just select R1 over here and run it. Yeah. So the run results are available. Go to the stream results and see. So as it is equimolar reaction, so there is no change in moles. And out of 200 kilomoles of ethanol, 136 moles have been converted. 73 remains for both ethanol and acetic acid. So this is how the reaction took place. Now let us see how plug flow reactor works in comparison with CSTR. So bring in the block for plug flow reactor for the same feed. So here again you have to use the duplicator. Bring in the duplicator over here. You have to manipulate with the feed line. So just bring it over here and reconnect the material streams in this fashion. And we have to rename it as P plug, product of plug flow reactor. Press next. So the specification for plug flow reactor is being asked. Here the reactor type, it may be reactor with specified temperature, or it may be adiabatic reactor, or reactor with all those specifications that we can specify. But for this particular reactor, we will use reactor with specified temperature, which is 70 degrees centigrade, as it was taken for CSTR. Now go to configuration. We have to give the reactor dimension for plug flow reactor, which is, again, we have done the calculation before, 2 meter and 0.3 diameter. So 2 meter and 30 centimeter diameter. And the reactions are already defined before. So just choose that reaction and your run is ready. So results are available again. Just go to the stream result of CSTR and add in the result for plug flow reactor as well. So unfortunately, we don't see any reaction to happen in the plug flow reactor, as if the feed has entered and it has come out of the plug flow reactor without producing any water or ethyl acetate. But that cannot happen. We must have done some mistake. Let us go back to plug flow reactor and see what mistake we have done. Yes, this is the mistake that we have done. The process stream we said vapor only. But at 70 degrees centigrade, we cannot expect water or ethanol or them will be in vapor phase and react. So we should write liquid only or vapor liquid. So if we don't give vapor liquid, then there won't be any reaction. So we just run it once again with vapor liquid and check the result. Yes. Now you can find some product, 140 and 130. Now here you can find that the amount of ethyl acetate and water produced in plug flow reactor with 0.14137 meter cube is more than that has been produced in CST. So this result matches with our understanding with the theory of CSTR and plug flow, that for the same size of reactor for plug flow and CSTR, the conversion in plug flow is more than CSTR, and that result is observed over here. Now we come to the final reactor that we have for this lecture, that is batch reactor, and we have to connect this inlet and outlet. We have to specify it as P batch. Now here you might be confused that it's a batch reactor, but we are giving a continuous stream of material. Actually, in Aspen Plus, we do not have any input that can be batch in the strict sense. We have to define certain parameters in the batch reactor setup, which will make it a batch from the continuous stream. Now let us see how we can make it batch. So press next. So we have to first specify the operating condition, which is constant temperature at 70 degrees centigrade, and we'll specify the reactor pressure, which is 1 bar or 1 atmosphere, I think. And we have to give the reaction kinetics, which has already been specified before, and the stop criteria, which is very important, up to what point the batch reaction should be continued. After that point, we should stop the reaction. That means that is the batch time. For that, we can select the reactor, this is the location, variable type, mole fraction. Let us assume that we will stop the reaction when the mole fraction of ethyl acetate becomes 0.308018. So 0.308018, that is the final point that we want to achieve for ethyl acetate. So we will say mole fraction stop value 0.308018 of component ethyl acetate and approach from 0. That means initially it was at 0, so from below, so 0 to 0.308018 it will go and calculate. Let us see, this is the criteria number 1, and we have only one criteria, we do not see any other criteria. And then this is the operation times. It is very important. This is the total cycle time. In other words, you can say it is a total batch time. Okay, so if we give 1 hour, then you can compare with the feed stream. The feed stream is so many 410 kilomole per hour. So if your batch cycle time is 1 hour, then your batch charge is 200 kilomole of ethanol, 200 kilomole of acetic acid, and 10 kilomole of water. That is your batch size. So by specifying the total cycle time, you are actually specifying the batch size. And here you make it purely batch. Okay? And the maximum calculation time is again important because most of the reactions are very fast. At least this reaction is very fast. From the experience, we can see the reaction is over within a few seconds. So we can say that we shall calculate only for 10 seconds with 1 second of interval in between them. Okay, so the specifications are complete. Now we can run and see how the batch reaction runs. So just go back to the stream results and add in the P batch and see it has stopped when the mole fraction of ethyl acetate is 0.3080. At this point it has stopped. So it is matching with the data of PCSTR stream. Now one more thing that you can see over there. Just go to the setup. Here you can bring in the composition, reactor molar composition of ethyl acetate. Press OK. So this is the composition you get let us make it finer calculation. So instead of 1 second, we make it 0.1 seconds and run the simulation once again and see the plot. Yes, now it is better. Now convert the time from hour to seconds. Yes, so you can see the reaction is almost complete within 2.15 seconds. And if you want to check the operation time, it is 2.1501 second. Beyond that, the operation doesn't take place, because by that time your preferred mole fraction of ethyl acetate is achieved. And this is the total heat load in joules, and heat duty also you can calculate in kilowatt. It is 1.222143 kilowatt. Okay, so that is how you can do the simulation for reactor models in Aspen Plus. So we end our lecture at this point today. Thank you.